This GeoHug session is proudly supported by Fleet Space Technologies. Daniel, it's time to wake up. It's time for GeoHug.
Oh, Griff. Oh man. Look. Before we get to the show, I just need to tell you about this dream I had. Right. So I was dreaming that I was using these 3D models to explore the Earth's subsurface.
That's not a dream. Have you heard about Exosphere by Fleet? It's a faster, more sustainable, and less expensive way to finding the critical minerals required for the energy transition.
Well, that's great because I've actually been having nightmares about the energy transition. But like, no, it must have been a dream because the models they didn't take months to make. It just took days.
Yeah, that's not a dream. Exosphere by Fleet can return a high fidelity 3D model of the subsurface up to 2.5 kilometers lightning fast.
All right, look, that all sounds great, but it must have been a dream because at the end, this is where it gets weird. So I
Mhm.
used the model, I looked at the Earth, I zoomed all the way out so I could see how the Earth looks from space, and it was flat.
No, that's a dream.
Okay, well that's good. But what you're saying is that Fleet has made my dreams come true?
I promise you are not dreaming. So if you want to take your search for critical minerals to the next level, reach out to Fleet Space Technologies and find out what more agile, data-driven exploration can do for you. So I am so happy to have Ali Sholeh with us today. So Ali is the Associate Porphyry Exploration Consultant with SRK Consulting. He has over 20 years of experience. Ali has participated in different international, regional, and district scale research projects with a number of organizations investigating many porphyry and epithermal prospects and deposits. He's authored and co-authored more than 20 papers and abstracts, including 2 major titles on the Journal of Economic Geology. So with his extensive experience, it is going to be amazing learning from him today about porphyry fertility for giant porphyry exploration with lessons from the Kerman Porphyry Belt. So this is going to be an amazing session. Please keep using the chat and we'll open up the floor at the end. And thank you so much, Ali, for joining. It's amazing having you here today.
Thank you, Jess. Hi, everybody. Today, we're going to speak about porphyry fertility studies and how we can use these porphyry fertility indicators for giant porphyry exploration. And we will give you some case studies from Kerman Porphyry Belt. First of all, I need to thank the sponsors of this research that is Laurentian University, Rio Tinto, University of Alberta, and national Iranian copper industries companies, Nisico. And I should definitely thank Jeremy Richards, who left us several years ago. And this research is actually one of the last research that we have done with Jeremy Richards during last 3 years of his life. And I owe a lot to him. I want to tell you that for any porphyry exploration, in general, for mineral exploration, we need to consider several class of factors. The first is formation factors. That is actually the answering the question if there is a porphyry mineralization for porphyry exploration formed here in this arc or not. And these factors include spatial distribution of mineralization, temporal distribution, some magmatism factors, type of magmatism, erosion, the oxidation of magmas, water content, sulfur content, chlorine, it's very important, sulfur, and many other factors that work on actually related on magmatism. The other tectonism factors, if it's, I mean, this arc is continental arc, island arc, if it's subduction related, is and the subduction speed, angle, depth, these all related to the formation of any porphyry mineralization. At the same time, we need to think about preservation. And so in preservation factors, we need to focus on post-mineral modification, like rifting, subduction, later subduction on arcs, I don't know, volcanism, several other things that might remove away or destroy a porphyry mineralization that has once formed. Exposure to the surface is another factor that should be considered in any explorations. By this, I mean uplift, erosion level, cover, later cover, thrusting, I don't know, sedimentation cover, volcanic or volcanic sedimentary cover that cover a porphyry mineralization. And at the end, exploration is also very important. Proper exploration and sufficient funding for exploration. This is very important because people always compare deposits, small porphyry deposits, and compare it to a big deposit without thinking of the volume of exploration that has been done. And so they conclude to some key things and say that, for example, a giant porphyry system should be like this because that smaller deposit has not those features. We should consider in less explored terrains the size of a porphyry mineralization mostly reflects the amount of the drilling program that has been on that, not the potential of the formation. You can see this in this map. This is the distribution map of global porphyry mineralization. You see most of these porphyries occurred in a linear trends that are actually along arcs, either island arcs or continental arcs. The older ones occur in shield that has high potential of preservation. The younger are along the continental margins, like what you have in North and Southern America, and also in North Aegean from Turkey to Indo-Asian here. If you, the last comment of my previous slide, speaking about the amount of exploration can be considered here. You can see there are numerous big porphyry mineralization in South and North America. I mean, these belts are very fertile for porphyry mineralization, but I think that one of the things that should be considered is that most of these are well explored, and there is a long history of exploration here because of the distance to the source of fund here, not necessarily the potential of the art to produce huge system. Although, yes, I mean, it's a very fertile art here. But if you do exploration, so there are no porphyry mineralization here in Africa because, I mean, the formation was, I mean, the potential of formation was low. Also, because there have been no exploration or very limited exploration here. Age distribution of dated porphyry deposits. Most of dated porphyry deposits are either Mesozoic or younger, with a big portion of Neogene and Paleogene. And porphyry mineralization can occur during the geological history, the geological time in different ages. But the thing of these actually graph that shows is that so we can expect formation of a porphyry system all along the geological history. Not all, I mean, after Precambrian. And but you know, the preservation of old porphyry systems are the issue that should be considered. It's a very good model of porphyry mineralization when you have a batholith at the root, and so there are some dikes that's bringing up magmas to shallower level to form cupolas. At the upper part of the cupolas, we have volatiles, and those volatiles, when gets enough room, escape from the top of the brine and goes into the rocks to form stockworks, mineralized stockworks. This is the literature, I mean, accepted porphyry model in literature. And speaking about the tectonic regime that is favorable for porphyry mineralization, it can form during subduction, collisional terrain, and post-collision, when you have slab break-off and upwelling asthenosphere that's bringing up and dehydrate slab to form hydrous magma that's required for porphyry formation. It's vastly said that porphyry mineralization occurred in compressional regime. This cartoon showed you that in pure compressional regime, you won't be able, I mean, the batholith won't be able to escape to go to ascend to the near surface to form cupolas and porphyries. And instead of shallow porphyry intrusions, you have big batholiths trapped at the lower part of the crust. On the other hand, if you have pure tension, like what you have here, you have lots of batholite, lots of basalts because of the fast ascending of magma coming to the surface. You have lots of basalts, and you need in a regional compressional regime and geodynamic regime, and some local extension component here that's called transpressional regime that's is very favorable for porphyry mineralization. So this is actually can be used a lot on a porphyry belt when you're walking on an arc. If you see lots of batholith, it means that you might be, I mean, the regimes might be something like this, or the erosion level is very deep. Or if you can see lots of basalts, it's killed the potential of porphyry mineralization there. So let's jump into the subject. What is porphyry fertility? So for porphyry mineralization, we need several factors to work together. And by fertility studies, we actually measure those factors to see if the magma could form a porphyry mineralization or not. So this is the answer to the formation question of porphyry mineralization. Those factors including if the magma is hydrous, if it's oxidized, because you need hydrous magma. High water content is very, very important in porphyry mineralization, because you know, the main factor of porphyry mineralization is hydrothermal alteration, for which you need water. So magma water content is crucial, and those water comes from the subducting slab from sediment, from water-rich sediments, ocean sediments probably. Oxidation of magma is very important. The magma should be sulfur rich, but it shouldn't be sulfur saturated, because if it's sulfur saturated, sulfur gets out of the magma at the early crystallization stage. So you have sulfides in gabbros and something, some rocks that actually crystallize at the earliest stage of magmatism. And it should be acidic to intermediate, I-type, magnetite series, calc-alkaline or alkaline. We have a class of alkaline porphyry mineralization. And since subduction to post-collision, arc magma. These are the factors that are important to porphyry mineralization, and for each factor there are some tools to measure it actually, and these all together called fertility studies. And the best and easiest fertility indicator of an arc is the presence of a porphyry mineralization. So if there is even one porphyry that occurs in an arc, you can expect more porphyry on the same arc. If the size of that porphyry was giant, so you might be able to find it another giant one. It is crucial and very easy. The other is I mentioned the importance of water, magma water content for hydrothermal alteration. So widespread hydrous magmatism is also very easy to determine and is very important. I'll show you how we use some tools to measure these factors. We use whole rock geochemistry, RE content of whole rock, and also RE pattern. We use mineral chemistry, zircon, apatite, epidote, colorite, alunite. Several minerals can be used for actually for fertility studies. I mean, the thing that is actually widely used is whole rock strontium over yttrium. We know strontium 2+ substitute calcium 2+ in pelagic clays and garnet. So in hydrous magma, because we have hornblende and yttrium partitioning hornblende as well. So we have hornblende crystallization before pelagic clays crystallization. So in hydrous magma, strontium over yttrium increase with crystallization. This is a beautiful graph that Locke's work on. It's a great paper. So he could classify porphyry-related rocks that has higher strontium over yttrium ratio because they were hydrous. The other utility is whole rock European anomaly. By anomaly, I mean we have a formula for that, European over European star, that is European normalized over the root of samarium multiplied by gadolinium. If it's more than equal or more than 1, it means that in the trend of RE pattern, you have no negative European anomaly or slightly positive European anomaly. That means that your European occurred as European 3+ because the magma is oxidized. European 3+, European 2+ substitute calcium 2+ in pelagic clays. In hydrous and oxidized magma, the European 3+, because europium occurred at 3+, it remained on the melt and enriched. So this is actually a good tool to use in terms of fertility studies. The other is RE pattern of whole rock. So in whole rock of fertile magmas and subduction related hydrous oxidized magma, I mean, like what we have in Serçeşme and Meyduk, we have lithuric shaped RE pattern, RE normalized pattern with higher light RE, flat MRE, and a sloping upward HRE. So this lithuric shape is actually very famous and very used in literature, and it can be measured by lanthanum or yttrium, lanthanum over samarium, and dysprosium over yttrium. These are the ratio that is used. As a case study, it's, I mean, the term adakite is also should be defined here. It's widely used and sometimes misused because it's actually related to the Adak Island, first of time that has been introduced. The word adakite was because of the strange pattern that andesite in Adak Island showed, and they call it adakites. And so adakites are not necessarily related to porphyries. There are some adakites that are actually related to porphyry mineralization. Adakites show pelagic clays or garnet crystallization, early crystallization. So these are different tools that used in literature by Richard 2012. Strontium yttrium, europium over europium star, different methods that could classify fertile and infertile magmas. So these are infertile magmas, these are fertile magmas for porphyry mineralization. It showed a good classification. Zircon cerium anomaly is also the same. So we have cerium 4+ and cerium 3+. In oxidized magma, the cerium 4+ replace zircon 4+. So if we have higher cerium anomaly in zircon, it showed that the magma was oxidized. That's actually a proxy to fertility that we used. Zircon chemistry is also very important. It is widely used. This is zircon europium over europium star, and this line is called reduction line. That's over this line, all samples are oxidized, and below this line of europium over europium star equal to 0.4. Below this line is reduced magma that is barren. So I will show you a bit later. And also cerium anomaly in RE trend of zircon is also the same, because higher cerium anomaly in zircon showed the fertility, showed the magma is oxidized, and you can use it as a proxy to fertility. So in summary, the important things of fertility study, the most important is magma water content. That so you need the magma to have more than 4, even 6, and sometimes 8% water content. You can understand this by the presence of hydrous phenocryst phases like hornblende biotite. If you walk on an arc and you see lots of amphiboles in different rocks, andesites, I don't know, granite, granodiorite, bathylites, so different phases, you can see lots of amphiboles, it means that the magma was hydrous enough to form a porphyry mineralization. The next question would be where to find it. I will give you a secret answer to this question later. So presence of hydrous phenocryst is very important. Abundant amphiboles, fractionation, suppression of pelagic crystallization is important, that it can be measured by strontium over yttrium or lanthanum over yttrium ratios, europium anomalies, and different methods. And for oxidized magma, we need to see magnetite phenocrysts in different rocks. It can be measured by Fe3 plus over Fe2 plus of whole rock, oxygen fugacity, amphibole composition regression analysis, immunomagnetic oxygen barometer, and different methods that can be used for defining oxidized magma. So it is also very important to consider the erosion level when you are studying fertility on an arc. So this is the literature accepted model for porphyry mineralization from Jeremy Richards, 2015, from top to the bottom of the system. Whenever you took sample and analyzed it, it showed you fertile for porphyry mineralization because they are from the same magma, same magmatism. So all of them are oxidized or water-rich, and so we can call them fertile. This is very top of the system, very shallow inside even northwest of Iran. There is a huge alteration, something like 10 kilometers by 10 kilometers, huge alteration system. Some epithermal under lithocaps. And so there are porphyry that has been confirmed by deep drilling, but it is deep and it might be huge. Sometimes you are at the deep part of the system that is potassic alteration, that is equigranular potassic alteration, which a low grade that is not good for anyone, something like 0.1% copper. That is, if you drill down, it will be the same or even worse. Sometimes you see some granular texture that is batholite, granular diorite batholite that's occurred at the root of the system. So if you want to look at the porphyry system, the porphyry might erode away fully, and the root has been exposed at the moment. And the perfect well-exposed porphyry potassic alteration. This is potassic alteration from Sachishme that has been overprinted by phyllic alteration. You might sometimes be lucky enough to find these things at the surface, but most of the times, exposed porphyry mineralization has been already discovered. So nowadays, during copper rush, you are dealing with these kind of potential areas, or even worse, it's somehow covered porphyry mineralization with blind exploration. So let's go toward Kerman Porphyry Belt. This is the map of Tethyan orogeny, including Neo-Tethyan orogeny and also Paleo-Tethyan orogeny, that occurred from Europe going toward Turkey, from northwest of Iran, Armenia, Azerbaijan, goes to the southeast of Iran toward Pakistan, and go to Tibet, China, and then Indonesia and down. So this belt formed during subduction and collision and post-collision of Neodymian belts. That during each stage of these, there are some porphyry mineralization occurring. The most important part of this area is central Neodymian belt that hosts several world-class porphyry mineralization. The central part is Iran, Armenia, Azerbaijan, and Eastern Turkey, and Western Pakistan. These are different magmatic belts and magmatic arcs in central Neodymian belt that each hosts porphyry mineralization. And we will discuss about Kerman Porphyry Belt that hosts Serçeşme, Miduk, Tahtkombat, other porphyry mineralization here. And so this is Urmiye-Dokter magmatic arc, and this is a portion of that that is called Kerman Porphyry Belt. We have Macron volcanic arcs that host Rekodik Sindek toward Iran that is Bidesakaristan. There are some deposits that's under exploration in Iranian side of the same arc. In Pakistan, it's called Chalgai Belt, but I mean, the better name for this is Macron volcanic arc, and it's related to active subduction of Macron that now is active. In Urmiye-Dokter magmatic arc and Kerman Porphyry Belt, the mineralization related to sin subduction toward post-collision of magmatism. And so the recent exploration results of NISICO showed some huge numbers, some giant porphyry mineralization, new exploration has done on it. So now the Serçeşme Sungun is 3.4 million tons, 3.4 billion tons at 0.48%. So it's a giant. Serçeşme is 3.1, Miduk is 0.8 billion tons. And so there are other centers near Serçeşme that is under exploration, including Anomaly B of Serçeşme that is 1.6 billion tons. Anomaly C of Serçeşme is, and Anomaly D of Serçeşme is 500 million tons. So this happened by extensive drilling during last few years. So on previous published data, Sungun was something like 0.8 billion ton, and now it is more than 3 billion tons, giant. This actually reflects what I said at the earlier slides, that I mean, these zones, the size of a porphyry reflects the amount of drilling, not the potential of that. So I believe that for example, in Sungun and Serçeşme, the mineralization potential is much more than this. So this is Sungun porphyry deposits, occurred 21 million years, and so it's huge, and it is recent drilling that the mineralization doesn't want to stop even at 1,400 meters below the pit, the pit bottom. So there are some other center near Sungun. When you have a giant porphyry mineralization somewhere, you need to look on their other prospects near that. So that's why there are some exploration here about in Kival, in Baluchi, in other areas that were, those exploration very successful up to now. This is the Kerman Porphyry map, and this is giant Serçeşme porphyry that's now it's 3.1 billion tons at 0.41% copper. Serçeşme map. Serçeşme is also not alone. You have anomaly B Serçeşme. This is Sereytun and other Serku anomaly C and Noçun anomaly D. These are all looking at the Serçeşme cluster, and they are all under exploration. So they expect more mineralization to be explored in near future. Miduk is another giant porphyry mineralization in this area. That so there are some drilling, recent drilling, more than 2,000 meters with 1% copper. It's a huge number. It needs more and more exploration. And this is called Sara mountain because it looks like a lady called Sara that's staring at the sky. I don't know why it's become stone. Maybe the first one who has discovered Meyduk porphyry was this lady, Sara, then become cursed. I don't know why. So this is deep drilling in Meyduk. And so there are older Takhtombat porphyry mineralization that's also porphyry, much smaller than these giant ones, and much older, is 24.2 million years. So with Jeremy Richards, we went to different places and took samples, for more than 40 samples from different magmas, magmatic rocks in the whole belt, and we grouped them into 9 groups. Some of them were porphyry related, some other were not porphyry related, and we separate those, and we got good results. So all these fertility indicators could distinguish fertile and infertile, porphyry related and porphyry unrelated mineralization. This is Serçeşme and Serçeşme regional and Serçeşme porphyry. You can see RE, whole rock RE pattern is a standout Serçeşme. We have Serçeşme zircon RE pattern that showed less European anomaly, higher cerium anomaly. And so we have mineralized Serçeşme related porphyry mineralization rocks that are above this fertility indicator rock of European over European start equal to 0.4. It's also the same for Meyduk. We could distinguish barren porphyry from fertile porphyries, and these are Rafsanjan area and Neogen area, where Neogen area showed some higher oxidation states and higher cerium anomaly and different European. So that means that these Neogen samples that there has no porphyry discovered yet related to these Neogen samples show very prospective trends. And this is also for the whole set of samples, we can see this. And European zircon, European over European star versus hafnium that show the trend of crystallization and the change of oxidation during the crystallization and magmatism. And so oxidized can be separated from barren and porphyry unrelated ones. While working on these graphs, I noticed some interesting things that I want to share with you. So this is European anomaly. It's not European content. It's European anomaly of zircon, and this is zircon age. And these are different rocks from different zones that are porphyry related or porphyry related here or unrelated here. So if you graph it, the EU anomaly versus age, it shows a nice trend of decreasing European anomaly with increasing age. That means that in Kerman Belt, the younger magmatic arc that you have, the higher fertility it shows, and the higher European anomaly and zircon show. It can be very useful in combination with actually erosion level study, because these are some prospecting neogen samples that showed no porphyry. No porphyry is discovered here, but there might be a bigger porphyry, bigger than these, like benefit, but it might be economic or not. So, understanding of erosion level is very important. If you use the other tools that showed fertility, it's also the same. This is lanthanum over yttrium, strontium over yttrium, europium star over age, and titanium as actually the showing the acidity of the magma with age. So all of these show that the younger in Kerman Porphyry Belt, the higher oxidation state and the higher water content of magma. And so if you plot size of these deposits with the age, it also showed a good graph that the older deposits and the older mineralization that you have, the smaller the size of the porphyry mineralization that you have. It has two actual understanding. First of it is that we have higher fertile magmatism at younger and more evolved stages of magmatism. And the other thing that should be considered is actually the erosion level, as I told you. So if there is a mineralization here, it's fully eroded. We have partially eroded porphyry mineralization. And so well-exposed porphyry mineralization occurred between 7 million years and 15, 60 million years in Kerman Belt. And so the biggest one is Serçeşme. It's not because it is potentially the biggest. It's mostly because it has more exploration done on it. So based on this finding, I think that here we have Kerver, Iju. These two guys could have the potential to be bigger and bigger by proper exploration. There might be mineralization at deeper part of it, but if they do proper enough exploration, these two guys can have their own place here. And this is, it's not related. So in summary, the main porphyry mineralization that is in Kerman, that is exposed to the surface, is somehow 11 to 13 million years. But I think there are some younger porphyry like Iju and Kerver that's still small and low grade, but it's not explored enough. All all fertile soils showed European anomaly more than 0.4 fertility indicator. And they have, I mentioned this, not important. So it is important to notice that in the Kerman Porphyry Belt and generally in all fertile areas and arcs, the younger magmatic soils are more evolved and more volatile-rich and more oxidized, and thus are considered more prospective for economic porphyry mineralization. And we should use this finding with a good understanding of erosion level. So the secret answer to the question of where to find a porphyry is that there is a porphyry at the end of each rainbow. You just need to find the end of rainbow. That's all. Thank you for listening.
I loved that. Thank you so much. That was an awesome presentation. So thank you so much for taking the time to do that.